Well, hello everybody. Now, in this particular case, I would like to tell you during the entire course of my lecture series, I had touched boiling on several occasions. Initially, if you remember, when I was dealing with macro channel flow patterns, I had shown you air water flow patterns, and then I had shown you steam water flow patterns when liquid, subcooled liquid or liquid at its saturation temperature was being introduced in a heated channel. After that, when we were discussing microchannels, I was trying to give you the criteria for defining microchannels. Then there was one criteria based on hydraulic diameter, there was one criteria based on suitable values of some important dimensionless numbers, namely the bond number and the confinement number, and then there was one other criteria based on bubble departure diameter, which again was a criteria pertaining to flow boiling in microchannels. After that, of course, during the discussion of the flow patterns and the effect of operating parameters on flow patterns, it was predominantly confined to adiabatic gas liquid flows and also for liquid liquid flows. Then when I came to the analysis part, I had first discussed the general analysis, and then I had given expressions and formula which are applicable to boiling two-phase flow as well as to adiabatic two-phase flow. Now, before I end this lecture series, I would like to just discuss some salient or some unique features of boiling two-phase flow in microchannels compared to macrochannels, and also boiling two-phase flow in microchannels compared to adiabatic two-phase flow in microchannels. So, we will present a brief discussion on this, and then we would be ending this particular lecture series. Now, well, before we proceed, it is very important to know the applications of flow boiling, and here I would you already know that I had already discussed certain things, that they are applicable in compact evaporator applications, and particularly in automotive air conditioning evaporators, then for compact condenser applications, and then there was a huge application for due to heat removal from high heat flux devices. Now, this is the most important application due to which flow boiling in microchannels has been receiving a lot of attention in the recent years. Now, why does flow boiling it is more attractive as compared to single phase liquid cooling? There are two reasons for it. The first reason is definitely even for single phase flow through microchannels, we find that the heat transfer coefficient is quite high. It is around say 10,000 watt per meter square for laminar flow of water in 200 micrometer channel. But we find that for flow boiling, the heat transfer coefficients are many times higher, as is evident from the data I have provided here. The other thing is, if you observe that, then you will know that the heat removal capability for a given mass flow rate of the coolant is much higher if the heat removal occurs by latent heat as compared to sensible heat. So, therefore, these are the reasons why flow boiling has received much more attention in recent years, and we will find that for flow boiling in mini channels and micro channels, the predominant mechanism is by nucleation. And if you observe, we find that there are two ways in which flow boiling can be expected to be implemented in mini and micro channels. One is two-phase entry after a throttle valve, two-phase entry after throttle valve. Now, very frequently this is particularly applicable to evaporators in refrigeration cycles. Now, the throttle valve prior to the evaporator, it can be designed to provide subcooled liquid entry, but more commonly it provides a two-phase entry with a quality varying between 0 and 0.1. This of course has got its problems. The first problem is the distribution of the two-phase mixture at the inlet headers. So, therefore, this poses to be a major obstacle in achieving stable operation, but anyhow this is practiced more or less. The other thing is subcooled liquid entry into the channels, and then gradually it starts boiling when it due to the heat which is being applied to the channel. This is of course an attractive option, because in this case the higher heat transfer coefficients associated with subcooled flow boiling can be utilized in these cases. But for both the mechanisms of initiating flow boiling in small diameter channels, for both of them the bubble nucleation is an important consideration. It is also true for two phase entry, because in this particular case also we find that slug flow prevails and nucleation occurs in the liquid slugs, and this is an important parameter for regulating the flow boiling in these particular cases. Now, just as I had discussed for adiabatic cases, the pertinent dimensionless numbers, I have just written it down for you just for your consideration. You will notice that we should be having some other additional numbers also. Now, if you observe the numbers which are important for flow boiling cases, you will find that for flow boiling, whatever numbers are there, except the boiling number, none of them considers the heat flux parameter. But this particular, the heat flux, this is particularly important if you have to consider the flow boiling cases. Okay. And because why? Because due to this particular heat flux, there is a change of phase from the liquid to the vapor, and this is associated with a large momentum change, which will be evident from this particular figure. Now, this figure shows an evaporating interface which occupies the entire channel, and we observe from here that due to the change of phase from liquid to vapor, it is associated with a large amount of momentum change. Why? Because the specific volume of the vapor is much higher as compared to the specific volume of the liquid, and due to this large momentum change, there is a resultant force which needs to be considered for a proper representation of the two phase flow characteristics, and also to understand the interfacial shape and its motion during flow boiling in mini and micro channels. So, therefore, this particular effect, it was first recognized by Kandlikar, and he proposed two dimensionless numbers which are commonly known as K1 and K2. If you observe these two numbers, you find that this is nothing but a modified boiling number, okay, where this has been modified by incorporation of the vapor and liquid densities, and K2, it relates the evaporation momentum and the surface tension forces at the liquid vapor interface. So, these two numbers, they are encountered during flow boiling. Along with that, the boiling number is also important, and I would like to mention also that just like I had told you in micro channels, we find that in this case the Yodworth number or the Bond number is not very important, because gravity or buoyancy force is not important in micro channels. It is just important to classify micro channels both for adiabatic two phase flows as well as for under boiling conditions. On the contrary, we find that the Weber number and the capillary number, these two are expected to be much useful parameters in representing some of the complex features of flow boiling. Now, if we consider the flow patterns and the rather how the flow patterns evolve in micro and milli channels. As expected, that the way I had discussed for adiabatic flows, in this case also we know that surface tension forces become important. Now, when surface tension forces become important, what happens? Let us see. This is the situation for a larger channel. In this case, there are a number of nucleation sites. Bubbles start forming in the nucleation sites. Initially, the bubbles are spherical, then gradually they start growing larger. As they start growing larger, they detach from the wall and they rise due to gravity. And then initially they remain as dispersed bubbles. As more and more bubbles are formed, they gradually coalesce to form the slug flow, and then finally all this slug or the plugs, they coalesce to form the annular flow. This I had already discussed when I was discussing the flow patterns in macro systems in a heated tubes. In this case, what happens, let us see. In this particular case, definitely just like the previous case, the bubble nucleates. Then as the bubble, with advent of time, the bubble that starts growing larger, the same way that had happened in microchannels. But in microsystems, contrary to macro systems, we find as the bubble starts growing, instead of getting detached from the wall, it cannot do this particular thing, because as it starts growing, it comes in contact with the upper wall, and therefore, it gets confined between the two walls and it cannot detach itself from the nucleation site. As a result of which, the flow patterns which we encounter here, they are slightly differently named in this particular case, and as you will observe, this is for a low heat flux condition. Initially we have bubbly flow, then gradually the bubbles, they start growing bigger and they flow as discrete irregular shaped bubbles. This particular pattern is known as isolated bubble flow. After some time, the bubbles, they start growing much more larger and they assume the disc shaped shape that I had shown. This is known as confined bubble flow. They are basically bubbles which are confined by the two walls and they cannot nucleate, and so they are driven off by the liquid also which is flowing, and finally these confined bubbles, they coalesce with one another at high quality and they gradually form the annular flow pattern. But there is one thing which I would like to mention in this particular case, that here there is, I will just show you this and then I will mention once more. So, this was the case for low heat flux condition. Now, at high heat flux condition, a very interesting thing occurs. In this case, what happens, as the bubble it starts growing, if you observe this, as the bubble it starts growing, the liquid is flowing in this particular portion and the bubble has to expand. It expands both upstream as well as downstream. If you observe here, in this particular photograph, we have shown the expanding bubble flow pattern, and we find that the way the bubbles are expanding, and if you observe the bubble expanding, you will find that the interface flows both in the upstream as well as in the downstream direction. Now, due to this, we get, or rather we come across a unique phenomena which has been specified or which has been termed as flow reversal. And this particular flow, due to this particular flow reversal, an additional instability sets in microchannels apart from the instabilities which are present in large tubes. In large tubes, we come across excursive and parallel channel instability, and in microchannel, apart from these two instabilities, an additional instability is induced due to flow reversal, and that also has to be considered. This is something unique for flow boiling in microchannels. The other thing which is important during flow boiling is, particularly in microchannels, in mini systems, as I have mentioned, we come across the confined bubble flow and the isolated bubble flow and then the annular flow. In microchannels, we come across two things. One is the phenomena of flow reversal and the other thing is an expanding bubble flow pattern. What happens? The bubble gets formed and then it keeps on increasing and it forms almost a tailor finger sort of a thing, and then it gradually occupies the entire channel when the entire liquid has vaporized. Now, here I would just like to mention that this evaporating or rather expanding bubble flow pattern has some differences with the annular flow pattern that we observe under adiabatic conditions. What is the main difference? If you observe the annular flow pattern, we find that here there is a flowing liquid film and a flowing vapor or gas core. While in this particular case, we find that the bubble keeps on expanding through the and pushing the liquid at the film, and this liquid film, it is basically it's stationary. It simply acts as a film under the growing vapor bubble rather than a flowing film, and therefore, the heat transfer mechanism is similar to nucleate boiling, and we find that there is a strong dependence of heat transfer coefficient on heat flux during flow boiling in microchannels, which naturally again hints at suggests the dominance of nucleate boiling. Now, the pressure drop and the void fraction characteristics, they are more or less similar. So, there is nothing to discuss, and as far as the heat transfer coefficients are concerned, what we observed is that there are a large number of discrepancies between the reported results. Some say conventional channel correlations are fine, some say they are not at all fine, some say they are fine under certain conditions and not fine under certain conditions. So, at the end I would just like to discuss the discrepancies, the cause for the discrepancies between experimental data and the correlations proposed for conventional channels, and that will be the end of this particular lecture series. The first thing which we observe is the temperature and velocity profiles, they keep on developing in the entrance region, and as a result the Nusselt number also starts changing along the microchannel, and therefore, it is very difficult to define a unique Nusselt number for the entire microchannel. Secondly, we find that there is a high difference in the fluid temperature between the inlet and outlet section. Now, what happens due to this? There is a variation in the thermophysical properties across the microchannel. So, naturally, if the thermophysical properties changes, it is very difficult to predict a unique Nusselt number. The third part is the rarefaction effects. Now, usually the rarefaction effects, they are present for the gas phase, and this is generally quantified by the Knudsen number. Now, in this particular case, if we find that for rarefied gases, the slip flow and the temperature jump conditions, they needs to be considered for rarefied gases, because they influence the Nusselt number. Slip flow increases Nusselt number, while temperature jump decreases Nusselt number. And particularly for gas vapor liquid flows, it is very important to consider these effects before we get a proper prediction of Nusselt number. Again, if we consider the compressibility effects, generally what do we postulate for compressible flow? That when Mach number is greater than 0.3, we assume that it is incompressible flow, and incompressible flow equations are applicable. But we must remember that this particular condition, this is a necessary but not a sufficient condition for incompressible flow, because although the Mach number at the inlet can be greater than 0.3, due to pressure losses, it may lead to density variations, which again can significantly influence the velocity and temperature profiles, and therefore can alter the heat transfer characteristics. And also there is another factor which is very important for small diameter or small hydraulic diameters, that is the internal heat generation due to viscous forces. Even in adiabatic flows also we find that this can produce a significant temperature rise, which again changes the fluid thermophysical properties, affects the heat transfer along the channel. And in order to evaluate the influence of the heat generation due to viscous forces, it is important to employ the Brinkmann number, where the Brinkmann number it is usually defined as the ratio of the heat, rather the ratio of viscous heating rate. The Brinkmann number, which is defined as the ratio of the viscous heating rate and the average heat transfer rate. So, therefore, in order to evaluate how important this heat generation due to viscous forces is, we need to employ Brinkman number to evaluate the viscous heating effects, and because we know that this also is going to influence the Nusselt number and the heat transfer coefficient. And over and above everything, as I have been mentioning, for all the experiments in microchannels for finding out flow pattern, pressure drop, void fraction, I have already mentioned there are large number of experimental uncertainties. So, therefore, these also are required to be considered for finding out, or rather during the heat transfer experiments in microchannels. So, with this I conclude the lecture series on adiabatic two-phase flow and flow boiling in microchannels. And based on the assignments and the presentation, you will be given an evaluation test, and you are free to ask all your doubts and all your questions while you are going through this course. Me and my TAs will be very glad to address them. Thank you very much.